Okay, so hello, my name is Paula. First of all, I want to say that I'm very thankful to be here and that today I'm going to present my talk that is using OpenCV and AI, practical image processing in Python. So the objective of this talk is to basically explain to you some utilities that I use with this library in Python. Of course, I will not cover like the whole library because it's huge, but I will show you what I use as an AI engineer and in the computer vision projects. So, okay. Okay. So first of all, I'm going to present myself and tell you why I'm doing this presentation. So hello, my name is Paula. I'm an AI engineer. And since I started studying at university, I've been interested in the world of images and more precisely images and AI. So the first project that I did was this one that is kidney disease detection in humans. So this was a collaboration that I did with the Hospital Vall d'Hebron. And in here, we were developing AI models for to detect diseases in kidneys and see if they are suitable for transplant. So I started working with this, so I fell in love with images. Then I changed job and I went to working at a startup in Barcelona, and we were working not with images, but with videos, and we were just trying to do some urban planning and urban analytics. Then right now I'm working at IAG and I'm doing more like a machine learning or Gen AI thing, so you don't have that many images here. But I also work in early disease detection in plants. I'm now collaborating with the dentist centers analyzing images of teeth. As you can see here, that it looks very weird, but it's supposed to show you the texture of the teeth here. I played a bit with stable diffusion. This is not working, but it's supposed to be tracking my face. So you can see that for me, images and AI is a passion, so that's why I decided to do this talk. So let's go. Okay, so now let's go to the main topic of the conference, that is the OpenCV library. So the OpenCV library is, I will quote what is saying in the official website, but is the world's biggest computer vision library. It is open source, it contains over 2,500 algorithms, and it is operated by the nonprofit Open Source Vision Foundation. And what can you do with this library? So basically, this library, I think it started only with more video and image analytics, but nowadays you can do everything that is related to computer vision. So for instance, you can do, of course, video and image analysis, you can do object detection, you can do face recognition, you can do image stitching, you can use deep neural networks, so you can develop your own deep neural networks, you can calculate the optical flows in videos, and much more. So in this slide, I put two images. This is the main page of the library. In here, there is the university of it, so you can also learn how to use it. I think there is free videos and paid courses. And in here is the module, so you can see the type of functions that you can use with it. Okay. Yes. So for this talk, what I did is that I created a code with some useful functions that I use every day now, but several times a week. And what I did is, okay, so let me share the code. So I created this GitHub repository that you can scan this. It's huge, but you can see the code. But in here, basically, what I did is that I create a Python code with here the library, where I will explain how to install the library. That is very easy, so I will not go through it because it's literally just doing pip install and you get it. And then, okay, let's switch better with the code. So, and then what you can see here is it showing? Oh, no. No. Sí. O sea, bueno, podemos... No, lo puedo abrir en la página web y ya. Sí. Bueno, ok. No, ¿eh?
Si no, dale 3 puntitos.
Espera.
Compartimos. Volver a compartir. Si mi puedes compartir aquesta finestra, jo he compartit la...
Sí, ara heu posat el repo al buscador, pero... Claro, pero voy a tener que ir otra vez a esta.
El problema es que, claro, vamos a tener que volver a la otra.
Sí, voy a tardar como 2 minutos.
¿La con este? Vale, sí.
Esto lo cambié de ahí, pues sí, lo puedes cambiar.
Vale. Okay, so you can see the code now? Yes. So, okay, this is the GitHub repo. And if you go to the main, well, okay, let's see how this works. So what I did is that I created a config file that you can see here. And basically here are all the functions that I implemented. So you can use these booleans to put true or false and see if, like, which one do you want to test out. So the idea of my code is that basically what I will do is that I will, so you can put true to any of these ones and it will show you the original image and how it is transformed after whatever thing that you want to do among these ones. So if we go to the Python code that is here, and you are seeing it, then you can see here, so basically here what I'm doing is, well, okay, all the imports, doesn't matter. So here we are reading the images that we want to transform. In this case, I'm using 2 because at some point I need 2. And then here we are getting the size of it, it's nothing fancy. And then, so here you will see like all the functions that I have implemented that I will go through them in a minute. And then here what you can see is that basically you will pop up the modified image. Sadly, I cannot show you how it works because it will not show here, but the code works. You can test it at home if you want. Okay, so this is not changing anymore. Okay. Maybe I will cover now all the functions and then I will show you all the images of the functions. So we don't need to go back and forth all the time. So, okay, I divided the code into types of functions. I put basic functions and advanced functions. This is something that I made up. It's not that OpenCV is saying that they are basic and more difficult ones. It's just that for me, basic functions will be the functions that you're using on operations and images that are just helping you feed these images to the models, but they are not adding any value to it. So it's just a matter for me to ingest the images. The advanced functions are the functions that are giving me some features. So they are giving me information from the image that I can use to train the model, or it's information that is valuable within itself. So here you can see, okay, so here we have this folder. And okay, I will go to basic functions. So in here, I implemented some of them that, again, are the ones that I always use. So I think they are useful. So first of all, I have the resize image. That this, I think, is the one that I will always use because you cannot enter directly the images to the algorithms or AIs or whatever. So you will always need to resize it. And it is also very important because usually, so nowadays we have high resolution images, but you never need so much resolution in your algorithms because you don't need 1,000 pixels. So you can just decrease the size of it. So in here, you will use this OpenCV function that is CV2 resize, and then you input the image and the new sizes, and it will resize it. You can try to maintain the aspect ratio if you just put the same size on divided by 2 or whatever, but you can also assign any random size that you want. Another function that is also helping decrease the size of the images is the grayscale. And this, I think I use it a lot because most of the times you don't need the colors of the images. So depending on what you're doing. If you're doing disease detection, then probably yes. But if you want to detect objects, a lot of times you don't even need the color. So in this case, I will use this function, and I will pass as argument this transformation. It is important to know that in this specific library, the way that you read the images is that you do the 3 channels that are RGB, but in this case, it's flipped and it's VGR. So all the transformations need to be from VGR to whatever color space that you want. Then, in order to improve the performance of the algorithms, sometimes you have few data available. So what you do is that you transform your images in order to create more data. So in this case, you will flip the images, or you can also rotate the images. So in this case, it's just rotating or flipping the images. It's nothing magic, but you will use these functions. Okay, I will go up. You will use this type of functions. For instance, if you want to flip, you will use this one. And in here as arguments, you just need to pass the direction of it. So it's pretty straightforward. In the case of the rotation, it is very easy when it comes to terms of rotating in multiples of 90 degrees. Kind of hard when it's not this amount of degrees, so I just put the easy one. But the other one is not so complex. It's just that they are matrices, so you need to transform the matrices. But in here, if you wanted to rotate the images, you will just use these functions to rotate, and then you can pass as arguments whatever degree that you want among the three that you can use. So not so many. And then this function is used for cropping. So this can be used in several ways. It can be used as data augmentation. So you have a finite data set, you need more data. So you start cropping sides of the images so you get more data out of it. So if you want to detect objects in a city, you can crop bicycles, pedestrians. Now I have trees, so you get more information from one image. You can also use it to get regions of interest. So for instance, if I want to detect smiles in people, I can just grab whatever images that I have of people, I will just put the face, and the algorithm is able to just detect, well, or focus on the face, let's see, for instance. And okay, this looks very silly, but it's very useful. So it's just a way to add text to the images, but this is very useful because in order to train models in AI, you need to have labeled data. So this means that you need to have images and then tell to the algorithm what is this image. Or when you are doing object detection in videos, you also want to know what is the object the algorithm detecting. So you will also use this type of functions that is just CV2, put text, and then in here you just pass arguments like the type of font, the width of the text, where is the text, and so on. And this function here, that I think is the last one of the basic functions, it's just to modify the pixel value of an image. So this can be used in different ways. I think this one is not even used in OpenCV. Well, you're reading the image using the library, but it's just the way that you can change the pixel values. But this one is very useful because you will use it to train the algorithm, so in segmentation, but you can also use it when you're doing diffusion models, because at the end what you're doing is that you're inputting images and you're getting other images out. So it means that the model is changing the value of each of the pixels. Okay, and now I need to go to the other part. I'm sorry. Okay. Now you can see the results of the code. Okay, so in here, this I will not go again because I already explained. So here we will just look at the images. So in this case, is how you will resize the images. So here you can see an example. I think I put here a random size. I think it was 500 by 400. I'm not sure. Then here is the result if you convert the image to grayscale. So you get exactly the same thing, grayscale. Okay, here we're adding text. I don't think you can even read it, but it says hi. And then, okay, here is the way to modify pixel values. So more or less. Oh, well, this is flipping the images. And then in here, you have the rotation of the images. Okay, and in here, the cropping. So, well, you can see here all the results of the code that you just saw. Okay, and now let's go to the advanced functions. So as I said, these functions are the ones that are giving you some meaning from the images. So, okay, maybe I can show you now the images and then the code, so we can be switching. Okay. So first of all, I used a lot the edge detection filters, and I think are the first ones that I started learning at university. So I think they are very useful. And so basically here, what you can do is that you have some functions in OpenCV that we will see later, that you can calculate the edges of the images. So in here, you can see that I applied two types of algorithms. And these algorithms, basically what they're doing is that they are taking the input images and they are calculating the difference of intensity of the pixels that they have in the image. So in this way, you can calculate the edges. Usually what you do at the beginning is that you will apply some blurriness to the image because of the same thing that I said before, that the images come with high definition and there is like a lot of pixel variation of colors, but it's really not needed. So you will apply first some blurriness, then you will try to detect the edges, so you get the edges that are really important and meaningful. And if you can see here, this one is supposed to work better than this one because it's applying another step that is a non-suppression algorithm. So basically here you're putting thresholds and you're saying, okay, I want you to be 100% sure that this is an edge. So you're putting 2 thresholds and you only get the edges that you think that are meaningful. Oh, wait. And this is very useful for all the things that I put here, but it's very used in object detection and object recognition because the edges is the positions of the image that gather more information. It is obviously very used in feature extraction. It can help you perform algorithms of noise reduction. Even though you're blurring it at the beginning, then you can like de-blur everything and you will get a much definition images in terms of the edges, of course. And then it can also help in data compression because I know that there are some algorithms that they don't even need the whole image. They can directly work with edges, so you're like saving lots of space. Okay, now the change of color. So this is also very useful, and I like it because you also get weird images at the end of applying it. But basically here what we are doing is that we usually input the images in the, you have the typical 3 channels that are RGB, but they don't have to be the ones that have more meaning for you. So you can you apply transformations to the colors. So for instance, you can use HSL or lab. HSL stands for hue, saturation, and luminance. So you can get the information of these 3 types of values in different channels. So you can work with each of them. You can adjust whatever you want, and it can help you with segmentation, or it can help you define things that you want to define in your image. The lab is also very useful in terms of so in this one, basically this LAB, what means is luminance, and then the A is the relation between green and red, and B is the relation between yellow and blue. So you can play with these values and then adjust the images to it. I use it a lot when I do disease detection. I use it with plants, I use it with humans, I use it with teeth, because it helps you get the values that you want or understand the content that the image is giving you. It's also used for color constants. So sometimes if you are working with videos, you want all the videos to kind of have the same coloration, because then for your model it's much easier to understand the objects on it. So you can also play with this. And it's also useful when you have problems with illumination and you want it to be invariant to illumination. So you will switch to another type of channel or even grayscale, and you will not have so much, the image will not be so affected by this type of things. Okay. This one, that is called ORB, that is oriented, fast, and rotated brief. It's a feature detection and description algorithm. So what does this mean? This is an algorithm that will take the input image and it will find the points that are more meaningful in that image. So this means that these points are the ones that you can use then to recognize this object. So for instance, in this frog, in order the algorithm to detect this frog in another image, it will look, or it is useful that it will have all of these points that you can see here. Well, I don't know if you can see them, but there are colorful points around here, okay? So, yes. And then, if you have this, so you know which are the key points of your image, you can also have this. So, well, here, you'll see I'm applying data augmentation because I didn't have more images, so I just flip the ones that I have. And then, if I wanted to recognize this object in a different space, I can use the key points that I found before. And now I can try to understand if this frog is the same one and where each of these pixels correspond. So this is very useful, for instance, when you have 2 images of the same thing but in different perspectives. So for instance, a building, and you want to have the full image. So you will use techniques like this in order to stitch the images together and create the whole picture of it. It is also very used in object tracking, because if you are in a video, you're tracking the same object in different frames, at the end are different images. But you can just use this, and it will tell you which is the person that you're looking for, or the car, or the bicycle. Yes. Now can we switch? Okay.
Ahora ya puedes pasar.
Ah,
Capaz que buscamos más cosas.
está bien, lo sacamos. Vale, perfecto. Gracias. Okay, so now we can see the code. So here, okay, you now remember the images that I showed you, and now I'm showing the code. Here, to perform edge detection, here I created this function. I'm only passing as argument the image itself and then which type of algorithm that I want to apply. And if we go here, the first step will be to transform the image to grayscale, because in order for me to detect the edges, I don't need the color. And then I will apply the blurriness. So I will use this function. Are you able to read? Okay, I'm sorry. Maybe I can zoom in. Is it better? No? See? Okay. Okay, so in here, I'm using this function that is the Gaussian blur. So basically, I'm applying a blurriness algorithm to my image. And then I can choose between two of the algorithms. So this is the Sobel one that was the most basic one. And what I'm passing as arguments are the image that is blurred. And then in here, I'm saying which is the depth that I want from my output. And then here, I'm indicating the amount of derivative that I want to do in my image. Because in order for you to detect the edges, you need to derivate the image. So here, I can say the amount of derivatives that I want to apply. And it will be for the x-axis and the y-axis. And this is the size of the kernel that I'm using. The kernel is a matrix that you're going to pass over your image in order to compute all the calculations. And here, you return the edges. In the case of the CANI, it looks more easy, but it's more complex to implement. But this is just a function. So here, we're just applying the CANI algorithm that is taking the image blurred. And then we just apply the two thresholds of ones that I'm saying that are useful for me. So we are just going to take the edges that are between these two thresholds. Then, here is the one that is the change color of the color space. Okay, and basically this function is very simple. So here I just put the type of color conversions that I want to do in this case. This is whatever of these ones. And then here you can see that I'm using the same function that I was using for the gray space, but I'm changing the argument. Well, this of course is this. So I'm changing the argument, and then you can convert to any color space that you want. Okay, now for the Earth feature detection. Okay. So again, as input, I'm just passing the image. And then again, I'm transforming the image to grayscale. Then I create the Earth detector, and I initialize it with 1,500 points. These are the points that the algorithm is going to detect in my images. So these are all the meaningful points that I will try to find. Then in here, I will compute the key points. And in here, I will use this function just to draw them so you can see them, even though you could not see them, but they were there. And yes, this is the function. And then in order to match these points to each other, so here, we are using both images that I showed you before. And then, okay, here. And then basically we are doing the same process. So we are initializing the Earth detector, we are calculating the key points, but then we are using these functions to match between the key points. Well, here we are analyzing, here we are matching, and here I am sorting the points for the distance. So as much distance that I get between points is that they are more different apart. If they are closer, is that they are the same point, or kind of the same point. And in here again, I will just draw the matches. So these were all the functions that I wanted to show you that are the OpenCV, and I hope that it will give you some ideas of different projects that you can implement. I wanted to show you a last thing that is a code. Well, I don't know if I will be able to show it. Oh, look at that. How it works. Okay. So I implemented this algorithm that is a gender and age detection algorithm that basically is using some OpenCV functions that are available. Wait, I will put this. That are available, and also it is using some pre-trained models because it's very hard to train models, so I'm just using pre-trained models. So we can go here, and I will show you quickly, more or less, how this works. So in here, we are getting all the models that I downloaded. So in order to do face detection with gender and age, you need 3 models. One that is detecting the face, one that is detecting the gender, one that is detecting the face. Okay, so we are getting the models, then we are initializing some variables. I'm saying the edges that I expect my model to recognize. So wait here. So these are the edges that my model will be able to recognize. These are the genders. And here I will start preparing my model. So in here, I'm using these OpenCV functions in order to load the pre-trained models. So basically, I'm loading the neural networks. Then I'm doing this, and then I'm initializing my webcam, in order, because now I will execute the code, and if everything works, you will see my face on the edge detection. And then here it will start recording the video. Here I'm calling a code that is basically just going to start and do the forward pass, so just the prediction of the face. That I will not go into that because it's very similar to what I'm doing above, so it's the same thing. And then, so from that I will get the detection of the faces. And then from the faces, I will go to all of the faces and I will try to detect the age and gender. So basically here I'm cropping the image so it just gets the face of it. And then here I'm creating a blob of the image. So basically I'm creating something that I can actually ingest to the model. And then I'm doing the forward pass, which is basically the moment that you're doing the prediction on your model. So we are doing this for gender, and then we are doing the same thing for age. Yes. And in here, I'm just putting the text so you know what the model is predicting. So I will... Ya está. Vale. Vale. Okay. And you can see that it works. More or less it works. The age is kind of crazy. Thank you. Okay.
Well, we have to leave the questions for the networking part. So thank you, Paula. And
thank you. Okay.
So take notes of your questions and you can ask later with pizza.
Desconecto tal cual.
Which is better than asking without pizza.
Oh, sí.
Sí, uy. Aquí.
Share, cast.
Is that a conference?
Nice.
Vale, llavors aquí sí, canvio pestanya, no canvia, ¿no?
Sí, lo que pasa que para cambiarlo, lo que le pasa a ella es que hay que actualizar. Entonces tienes que salir, eso es lo que le pasó a ella. Hay que stop. Entonces ahora volverlo primero, primero.
Ah, perdón. Cambiar de pestaña,
exacto,
¿no?
Primero poner el source, parar. Y ahora confirmarse aquí. Ahora ya sí.
Y ahora ya puedo cambiar de pestaña. Ah, mira.
Much faster. We learn something.
Vale. Y aquí va el VS Code, ¿no? Vale.
¿Y si vos a clicar?
No, no. Ah, sí, sí, puedo. Sí, sí.
Però sí, és que ho posem al davant, que serà més fàcil.
Perfecte.
Personal.
I... Això hauria de...
Espera, que s'està enfocant.
Mira que no. Sortia verd, però no m'interactuava... És a dir, hauria de passar màgicament, només per estar connectat aquí.
Sí, potser no.
No,
està encès.
El USB?
Sí.
Bueno, puc passar jo. No passa res. I això està encès tot...
Ara.
Ah,
Bueno, ara sí. Digue-li que tanca i ja està.
Quin botó he d'apretar exactament? Jo no tinc aquest botó.
S'ha de salir.
És continu o...
No, sortir.
Ah, vale. Vale, perfecte. I això perquè ho tinc, llavors? Eso, vale. Hello. I'm David Masip. I'm data manager in Glovo. And yeah, today we're going to talk about A/B testing. Thanks to PyVCN for organizing this and giving me the chance to talk. I want to start with a raise of hands. Who in here has run an A/B test in their life? More than 5 A/B tests? Okay, good. So I'm for the ones who haven't, I'm starting with a refresh on A/B testing. Okay, this is like the introduction to the talk, and then we're going to go to the main topic of the talk. So what's an A/B test? An A/B test is a tool that we have to measure the causal impact of an action, of changing something in, for instance, in an e-commerce platform, no? And the way we run A/B tests is we use randomization. This is like the key thing to run A/B tests. We randomize users, and some of them get our old treatment or control, the thing that we are currently doing, and some of them get the new thing, and we essentially want to measure the impact in some metric of doing this new thing versus the old one. So we start with randomizing users. Some of them receive the treatment, some of them receive the control. And then we run the test, we collect the data, and when we have data of some users that were in treatment and data of some users that were in control for a particular metric, essentially we use hypothesis testing to see if the mean of that metric was different in treatment and control. So this is key. We use hypothesis testing. And what many people do is you have your null hypothesis, which is both groups had the same mean, and then if your data shows that your groups are very different and have very different means, and we do this with p-values, then you reject the null hypothesis and understand that there was a change in the means. And this 0.05 that we usually take to decide if there was a change or not in the p-value is not a fixed thing. You can actually change it, but when you set this threshold to 0.05, what you're saying is my false positive rate is 5%. False positive rate is I'm going to run 100 tests that have no impact, and on 5 of them I'm going to say, yeah, I did something. No? So like the idea is that you want this number to be low. You want when you don't change anything, you don't want to say that you changed something, no? And we want to keep this low, and in general we keep it to around 5%. So this is how like the A/B testing procedure usually works. Then, and this is what we're gonna talk about today. There are quite a lot of things. We're gonna talk about power analysis through most of the talk, and then a power analysis library that we've written at Glovo, and it's open source, and then some experiences that we had developing this library. So, like I explained more or less what an A/B test is. Like the first question that you have after like understanding what an A/B test is how long should my A/B test run? And this is what we're going to try to answer in this talk. And actually, there are a lot of questions that are not the same, but they are also answered with power analysis. So how much traffic should I put to B? I don't need to do 50-50. I could do only 5% in A and 95% in B or other splits. like how wide should my test be? In how many cities should I run my test? Should I use this 5% or 10% threshold for rejection? Should I use variance reduction? Should I stratify my treatment allocation? So there are many questions that can be answered with power analysis, but the main one that we are focusing in here is how long should I run my A/B test, which is probably the most important question. And this depends on a lot of things, no? Like the amount of data that you have per day, the effect that you're interested in measuring. So in general, if you want to detect a very small effect, you're going to need to run a very long experiment. And if you are only interested in detecting huge effects, you can run shorter experiments. How your data is distributed, the hypothesis test that you're actually running, and yeah, the statistical significance of the test. And then, very connected to experiment length, there's this concept of statistical power. And here you can find the Wikipedia definition, but also like my definition, which is the probability of detecting an effect when there is a real effect. In general, you want this quantity to be high. In general, you want to, if you have a real effect of your feature, you want to be able to measure this real effect in most of the time. So you want this power thing to be high. And this is connected to experiment length in the following way. So this is the power for a given test and the number of weeks that you run the test for. In general, when you have a lot of data, when you have essentially more weeks where your tests run, your power increases. And if your test is infinite, your power is going to be 1. So like this is why we talk about power when talking about experiment length, because the longer the experiment, the more power you have. And this is essentially how people decide about experiment lengths. So they set an effect, and all this line is depending on the effect size. So what people usually do is they decide on an effect size. So I'm only interested in changes of my conversion rate of 1%. No? So you take this 1%, you calculate the power line for the 1%, and you decide on a level of power, like 80%, for instance, and you choose the minimum number of weeks that will give you this amount of power. So in this case, if we want power 80%, we need 7 weeks of test. If we were less ambitious about our power, we are only interested in 60%, maybe 4 weeks and a little bit would do. So this is in general how we decide experiment lengths. And you can see that power does not only depend on the experiment length, but also on the minimum detectable effect or effect size. So in general, if you're interested in bigger effects, you're going to need less weeks, and if you're interested in smaller effects, you're going to need more weeks. So this is how we usually do this. And then, yeah, power is related to, we talked about type 1, well, false positive rate, which is the type 1 error. Power is related to the other error, which is called type 2 error, which is the probability of, the type 2 error is the probability of not detecting a real effect when there is a real effect. So in general, what people do is they fix the alpha using this threshold on the hypothesis test, and then the power and beta depend on the experiment length. Okay, and how? So we draw all these nice lines, and then how do we actually calculate power as a function of the number of weeks? This is what we need to decide to know experiment length. And then if you look in the internet, there are all these formulas, and you can apply them. So this will give you the power given an effect, which is this theta, and the number of observations. You can map this number of observations to days in your experiment, and then get power, and you're going to be able to draw these lines. So this you can do. The only issue with this is that this does a lot of assumptions. So it assumes that you're going to run a t-test in the end to compare the difference in means. It assumes that you have this particular formula assumes that you have a 50-50 split So if you want to do fancier things like a test where you don't split by customer, but split by city, this doesn't work. If you want to do variance reduction, this doesn't work. If you know that the feature only acts on some users heavily and not so much on the others, this doesn't really apply. So this is super simple to do, but very specific. And if you're like me and don't know a lot of statistics, there's like a lazy solution, which is simulation. Actually, you can very easily simulate these power lines, and we're going to explain how. And you don't need a big amount of knowledge on the hypothesis test. The only issue is that this is slower. So this one, Python calculates 1 million of these in a second, no? And the other one, we're going to see that for every effect and for every experiment length, it takes like a minute, depending on the data that you have. So the issue is that it's slow. But and I've read this online. They call this an embarrassingly parallelizable process. So it's very easy to parallelize. So if you have a cluster or something, you can run it way faster. And this is what we're going to talk about now. So keep in mind what I said at the beginning. The power of a test is the probability of detecting an effect if there is a given real effect. And this is what we are going to simulate, okay? So we take some historical data. This is the distribution of a metric like delivery times in Glovo. And we simulate with our historical data the split that we're going to do in the test. So we have some customers going to A, some customers going to B. And then the thing is that we create some fake data, and that's why we call it simulation. So we take the treatment data, which is the B, and add a fake effect, okay? And the size of the effect that we add is the MD, the minimum detectable effect, the effect that we're interested in measuring. So we add a real effect, and then we have data as if we had run an experiment. It's fake, but it's like experiment data. And we can run an hypothesis test on this data, and we can get a p-value. So the idea is, and we can say, in this case, there was a real effect, and we were able to reject it because the p-value is like less than 5%. And we can do this many times. So we can do different splits of the data, so all of them are random, and we're going to get different rejection decisions. So in this case, we were a bit unlucky, and it seems that there is no difference, so the p-value is super high. And the idea is this: we repeat this like 100 times, and in the 100 times, we get 100 different results, and in the end, we take this. We have, for each time that we run, we either rejected the null hypothesis or accepted. We take the fraction of times we rejected the null hypothesis, and this is our estimate of power. This can all be seen in this figure. So you split data, you add an effect, you run the hypothesis test, and you have a rejection or acceptance. And then the power is the percentage of times you rejected. Because in these 100 times, we actually had a real effect. We took data and we added the real effect. So our estimation of power is the percentage of times that you were able to reject this. And you can see that this, compared to the previous one, this is very slow. For a given effect, we had to run these 100 simulations. If your data is relatively large and your hypothesis test is relatively slow, this is very, very slow. And this is the pseudocode of what we did. No? So we do n simulations. In each simulation, we split the data in A and B. We add a fake treatment effect to the B data, and then we calculate a p-value. And we say, do we reject? And we do this many times, and the power is like the mean of the rejection rate. Okay, so this is the idea, and this is what the library does. So we wrote a library to do this function. And it seems stupid, but actually there are many ways to split the data. There are many ways to add effects, and there are many ways to analyze your A/B test data. So the library, what it tries to do is accommodate for many possible ways of doing the the three things. But in the end, what it tries to do is this function. And remember that this was to draw these power lines and to know the experiment length. This is the hello world of the library. So the easiest way to interact with this library is with dictionaries. So you have a configuration and you tell it, hey, I have a way to split my data, which is non-cluster. This is regular splitting, like regular user splitting. Then you have a way to add this fake effect, which we call uniform. The name is not great, but it means constant. We add the same effect for all the treated units. And then we have an analysis method, which in this case, it's a very long name for a t-test. This is a regular t-test. So we define this dictionary, we create a power analysis object, and then we run the power analysis method with a given effect. Okay, so this is, and this data frame is some historical data. Now you would take this data frame for different experiment lengths, like the data of last week, data of last 2 weeks, data of last 3 weeks, and you would run this, and this will give you this power line that we were showing at the beginning. As I was saying, there are many ways to split the data. So there's a regular splitting, imbalance, stratified, and cluster splitting. Some ways to do perturbations on your data. For instance, for binary data, you don't want to add a constant effect, but you want to flip zeros to ones and ones to zeros. And then there are some analysis methods like ordinary least squares, generalized estimating equations, clustering methods. And it also supports variance reduction. And what I think is very nice is that it's easily customizable. And I'm going to go now. But before that, there's some online documentation, many toy examples, and extensive unit testing. The unit testing, when developing this, was super important because people use this in Glovo to assess experiment length. And whenever I hear about the hint that there's a bug in this method of the library, I freak out a lot because it's like, because of my crappy code, someone is running a 2-month experiment when they could run a 2-week experiment, no? So yeah, the unit testing was super, super important. And yeah, so the structure of the library is more or less this. There's this power analysis class, and then there are these 3 kind of abstract classes. The splitter, which is what splits the data, the perturbator, which is what adds this fake effect, and this experiment analysis, this is the hypothesis test. And the power analysis, one power analysis class has a splitter, has a perturbator, and has an analysis, and then it runs the power analysis using the function before. So yeah, this is how it works, and some people have some splitters that are not in the library. So what do? The idea is that you can create your own experiment, for instance, experiment analysis that has this analysis p-value method, and this will perfectly work with the power analysis thanks to the abstract classes and the composition. So if one good thing about this library is that if there's a method that is not in the library, you don't need to call the maintainers. You just need to create your own class and plug it in the power analysis. So this is true for the experiment analysis. This is true for the splitter, and this is true for the perturbator. So if you're missing one of the classes, you can just write it yourself in your user code and plug it into a power analysis. And then I want to keep with some learnings on Python. This is more like the Python side of the talk, not so much about statistics and power. And yeah, I'm going to show a couple of things I encountered while writing this library. One of them is the test docs library. it's actually quite simple. It's these MK test docs, and essentially what it allows you to do is to run this check docstring method that will take all the docstrings in your class, run them, and if it fails, you're gonna see it in your test. So it's a super bad user experience if you take code from someone, check the docstring, copy it, and it doesn't work. No, so this is like whenever I have to write libraries, this is like a super good practice to me because I don't want users to take code from the docstring and it doesn't work. So this is, and we've caught many bugs with this. Like you are writing your docstring, you don't pay a lot of attention to the docstring, and then it's broken, no? And similar with the README. The library has a README with many examples, and you don't want them to break. So with this test docs library, what you can do is test a markdown file. So essentially what it does, it takes all the Python code in that markdown file, it runs it, and it checks that it ran properly. So this is the first learning. And then the second learning is this PyTest slow last. So I'm gonna do a little demo. So I'm gonna run PyTest on the library. And it takes a little to collect the tests. And you're gonna see, okay, it's running test docs, which is super slow. This is the test I was showing before. This takes a lot of time. And when it finishes with test docs, it's gonna start running all the other tests that run, most of them run blazingly fast. So most of them run in less than a second, but I have these 3 annoying tests in test docs that take like 20 seconds, and you're gonna see some test power analysis that takes 20 seconds as well. So this, as I was developing this, was super frustrating to me because I changed something in a file, and then I had to run these test docs that took like a minute, and I couldn't check fast if my changes worked. It's actually worse than I remembered. And now it's gonna run super fast. So the last ones are super fast. It took 70 seconds, but most of the time we're waiting for these test docs. And I got fed up with this. I got this from a PyTest book that you can implement your own hooks on PyTest. And I implemented a hook that is called slow last. So essentially what it does, it takes the durations of the tests of the last test run, and it first runs the quick test, and it last runs the slow test. So let's see if it works. It takes a bit to collect as well, but now you're gonna see a lot of tests running super fast, because in the last run they were the fastest test, and you're gonna see that the test docs only run at the very end. So you see that we already have like 90% of the tests have already run, and in the previous case, 90% of the tests only run after 40 seconds, and we still have some tests running. In the end, it's going to take the same 70 seconds, but you have faster feedback on your fast test, and in the end, it's going to take the same. And probably it's the test docs that is super slow. So this is, I recommend reading this PyTest book. PyTest is super good library, and it's not that hard to implement your own hooks. Okay, these were my Python learnings doing this, and now I have a section of meta learnings during the development of this library. So I think something that we did well from the beginning is starting the README with a hello world example. It really helps users to, you send them the link and they already can run the first thing and start tweaking according to their use case. So if I write a library again, this would be one of the first things that I do. Then this library was written because I was doing the same thing 2 or 3 times and I got fed up and I was engaged with it because I was the main user of it. So this is super good if you want to be engaged and work for a long time in a library, that you are a user of the library. And then the thing that I was saying before, if you empower users that make them independent from you, then it's also a huge win, because they get to know the library deeper because you allowed them to build within the library. Then things that I'm very upset about. Library name. So it started as a library to run and analyze cluster randomized tests, which is these CT tests that we have to run at Glovo. But then I started changing it to a simulation power analysis library. But the name is something quite hard to change. So think about the use case and potential of the library, and then give the name according to that. Because like the name still sucks and cluster experiments, and I couldn't change it. Then also some things that I didn't think about enough is names for classes. So like this method, assign treatment df, what it does is splits data into A and B. So this method should be named split, not assign treatment df. And well, I didn't think enough, so I put this name, but now when this is open to the users, so it's not that easy to change. And being a simulation library that depends on randomness, it took like a year to add seeds. So if you do some library that has randomness in it, add seeds as soon as possible. And actually, some tests are still not seeded. So when I run these demos, there's some slight probability that one of the tests fails. So I'm a little concerned. And then, so yeah, I copied the template from somewhere using setup.py, and I've had issues because they are kind of deprecating it. So if you have to start writing a library, use poetry is much more up to date, and you don't have to do patches for setup.py to work. And then some things that I think you need to do if you want to have a library that is used is first track users. At first, I didn't really know who was using the library, and there's this GitHub search query that allows you to search in an organization for a name, and with this I've been tracking how many people use the library, who uses it, and it, well, if you have any issue that you have a bug, you can communicate taking the users that do this. Second, try to sell it, because if you just develop a library, nobody cares. And so this is a problem that we have at Glovo running this experiment length analysis. So I've been trying to help people do this, and it's always super easy to tell them, hey, there's a library that does this. And then in the same way, people are not gonna contribute just because they think it's cool. So sometimes you have to really chase people when they give you some issue that, okay, I had this issue with the library. You have to enforce, like, okay, can you actually solve it? And that way is much better, because they get used to the library and they sell it. And this is the references that I'm going to share later, and then 3 takeaways, and I'll share up. So first is that the framework to decide experiment length is power analysis. So if you need to decide on the length of an experiment, use it. If you don't have trivial tests like 50 A/B customer tests, you can use simulation. If not, it's going to be very hard for you. And if you see something that many people are doing often in your library, in your organization, you can write a library and solve the problem at scale. And yep, that's it.
Maybe we can do a question or two. Any questions? Raise your hands.
What are you using this for at Glovo?
What's that?
What are you using this for at Glovo?
In the?
How are you using the A/B testing for your business?
Ah.
What benefits?
Pues, hola. I don't. So we use it for almost everything. Like any change that we do, we try to A/B test to first measure the impact to know if it was a positive or negative change, and then also to track the impact that teams are having. In the end, if a team is running tests that have huge impact, maybe it's an investment opportunity, and if a team their tests have 1/10 of the impact, it justifies less of on an investment. No, but to me, the first application is when you do a change. Did it work? Did it worsen things? Did it improve things? So this is and it's any like product configurations changes, operations changes, all that we can test, we test. No.
More questions, or should we pass to the food?
Let's say that. Let's go eat.
Thank you, David.